Alrighty. So today we're going to do sections 5, 4, and also I'll probably do 5, 5 with this one as well. 5, 5 was just me talking. There's really no examples for it. So as I said in the emails, I'm cutting out chapter 9. There really isn't too much we can do with chapter 9. And it's probably better. So I'd rather you use the extra time to go back through chapters 1 through 5 and make sure everything's kosher before you head into the final. And I'll be sending an email, I don't know, tomorrow, Friday, of what's going to happen with the final. Okay, so chapter 5, 5.4 specifically. 5.4 is the greatest common factor and the least common multiple, the GCF and the LCM. There are going to be basically 3 ways to find the GCF, and there are 2.5 ways to find the LCM. I do not care which of the ways you use when it comes to the final. So of the various ways, just pick one and focus on that. In the homework, it's going to say to use specific methods, but 1, there's no way for me to check, and 2, it sort of defeats the purpose. Just pick the one way that you like the best and go from there. There's one way that I like the most because it does both the GCF and the LCM, but that's my preference. So let's start off with me loading up my notes because I didn't do that. So I will just make some music. Okay, it's already loaded. That didn't take long. And I'm scrolling. Aren't you glad you're hearing this? You're scrolling. Scrolling. Is it the first one? All right. All right. Let me just make some copy and pastes there. I'll put this in this one. There we go. I could have seriously have done all this already, but you know, that would take foresight and all that stuff. I'm almost there, I promise. I'm not. I just want you to believe that I am. Okay. There we go. Okay, that's good. Alright, so let's start off. Finding the GCF, the greatest common factor, using the prime factorization method. Oh, there's an extra left parenthesis there. There are 3 steps. Factor each number into primes. So this is where your divisibility tests will come into play. Pick the primes that only appear in each factorization, raising each to the smallest exponent that appears in any factorization. Now that part's tricky. That's why we'll do an example, then I'll send you off to Videoland. And then the GCF is the product of these primes to their powers. Okay. Alright, let's make up some numbers here. Let's pick some good ones. Suppose we had, like, I don't know, 136 and 48. So we are looking for the largest number that divides evenly into these 2 numbers. Hopefully it's nothing boring. We'll find out together. Oh, you know what? I'm going to, instead of 136, I'm going to make it 1362. I like that better. And then we'll make this 486. All right, I like that better. Okay, so 1362 is obviously even, right? So that means it must be 2 times something. 2 times what? I don't know. Bust out your calculator. I mean, that's why you bought one. I hope you bought one. All right, 1362 divided by 2 is 681. Oh my gosh, I hope that's not prime. It's not working. All right, 681 is no longer even, so we can't use 2 anymore. But notice 6 plus 8 plus 1 is 15. 3 goes into 15, which means that 3 must go into 681. So that was your divisibility test for 3. Oh. Sorry, my UPS delivery arrived. Okay. 681 would be 227. Oh, who picked these numbers? All right, so 3 times 227 is 681. Okay, 2 plus 2 plus 7 is 11, so that means 3 doesn't work anymore. 4 won't work, 5 won't work, 6 doesn't work, because 2 and 3 must both work. 7, you had your rule for 7, which I'm way too lazy to try. 8, nope. 9, nope. 10, nope. 11, I don't think 11 works. So here's a little trick, and I don't know if this is mentioned in the book or not. The numbers you have to try are up to the square root of that number. So the square root of 227 is 15 something. So you only have to try your numbers up to 15. So I did 11, 12 won't work. 13, let's try 13. Nope. And let's try 15. Nope. So that's it. 23227. Wow, exciting. I know. It's like, something to watch because there's no sports anymore. All right, so let's do this one over here. 486. Definitely 2 will work. And this will give us 243. Oh, no. Are we already in trouble? 2 plus 4 plus 3 is 9. So that means 3 will work, also 9. So that's good. This would be 81. Okay, now we're cooking with something. And then 81 we can say is 9 times 9. And then in each of these 9s are both 3s. Does the order in which you break it down matter? No. Let's suppose for 486 you said, clearly the number 9 works. And you broke that down as 9 times whatever that would be. That's fine. Everyone should still end with the same factorization. So 1362 is the same thing as 2 times 3 times 227. 486 is the same thing as 2 times, we have 1, 2, 3, 4, 5 3s, so 3 to the 5th. Okay. So step 1, factor each number into primes. Check. Step 2, pick the primes that only appear in each factorization. All right. So notice that means only pick the primes that are common to both, their intersection. So notice they both have a 2 and both have a 3. 486 does not have a factor of 227. So we only look at the 2 and the 3. That's it. Boop. Step 3. The GCF is, and then we have to do the powers. And then raising each of them to the smallest exponent. Well, here the 2 is to the first. Here the 2 is to the first. So for our GCF, we take the 2 to the first. Here, 3 is to the first. 3 is to the 5th. Which one is smaller? The 1. So we take the 3 to the first. We can't look at the 227 because it's not a common factor in both. So the GCF is the product of these primes to their product power. Well, 2 to the first times 3 to the first is 6. So the largest number that divides into both 1,362 and 486 is dos. Is 6. It's been a day. It's been a day. Okay. So let's make it, where am I at? Let's do this real quick. Let's suppose I had 2 numbers. And oh, can I erase here? I can. You know what? I'm going to get rid of this one. Okay, so let's suppose I had these two numbers, 2 cubed, 3 squared, 5 times 11, whatever that number is, don't care. 2 to the 4th times 3 times 5 times 7 times 11 squared. Okay, the GCF, we start off with factoring both numbers, which is already factored for us. That's great, so step 1 is done. Step 2, what factors are common? So you don't look at powers at this point, you're only looking at the bases. So they both have a 2, they both have a 3, they both have a 5, and they both have an 11. They both don't have 7, so we can't include the 7. All right, and now you take the smallest exponent of just those powers, those factors. So 2 to the 3rd, 2 to the 4th, we take the smaller one, 3. 3 to the 2nd, 3 to the 1st, take the smaller one, 1. 5 to the 1st, 5 to the 1st, we take 5 to the 1st. 11 to the 1st, 11 squared, take the smaller one, 11. So 2 cubed is 8, times 3 is 24, times 5 is a number, times 11 is another number, and whatever that number is, that's the GCF. Okay, if you would, boop, please watch video 59. And then after that, I'll show you another way to find the GCF. All right, so then the second way we're going to learn how to find the GCF is by dividing by primes. Oh, well, let me erase that. That's weird. As it says there, you have some steps. Write each of the numbers in a row. Divide each number by a common prime factor, Continue to divide until the quotients are relatively prime. Oh, someone forgot to explain what that phrase meant, but I'll do that in a second. And the product of the primes factors gives the GCF. Okay, two numbers are relatively prime if their GCF is 1. So if you had two prime numbers, like 7 and 13, what's the largest number that divides into 7 and 13? You would say 1. So that means 7 and 13 are relatively prime. Relative, meaning to each other. Prime, biggest factor is a 1. Okay. But they don't have to be prime to be relatively prime. For instance, let's look at 8 and 9. 8 is 2 cubed. 9 is 3 squared. But what's the largest number that divides into both 8 and 9? You would say 1. So because of that, 8 and 9 are relatively prime. Okay, very good. So let's try, let me make up some numbers here. We'll say 410, and we'll say 300 and, I don't know, I don't want to do 410. 440, that's good. And so we'll say 320. I like it. Let me erase the 440 because it looks icky. So what you do is you look at these two numbers and you think about a prime number that goes into them. They're both even, so we can pull out a 2. So 2 goes into 440 220 times. 2 goes into 320 160 times. Hooray! Now you look at this row, 220 and 160. What's a prime that goes into them? Well, they're both even yet again, so we can say 2. 2 goes into 220 110 times, and to 160 80 times. Hey, look! They're still even. We can take out another 2. 55, 40. Hey, look! They're not even. So now we gotta switch gears. 55 and 40 end with numbers that dictate divisibility by 5. 5 goes into 55 11 times and into 40 8 times. Now notice that the greatest common factor of 8 and 11 is 1. And because the greatest common factor is 1, then that means these two numbers are relatively prime. So that tells the viewers at home, stop. Ignoring these numbers off to the side here, their product is the GCF. 2 times 2 times 2 times 5 is 40. So 40 is the largest number that divides evenly into 440 and 320. So we could have used the prime factorization method, the first one, or here's another method, finding the greasy commonest factor by dividing by primes. Both methods are great because they could find both the greatest common factor and the least common multiple. They both have to have a little procedure to make you to be able to find the least common multiple, but you can knock out two. Well, let's not kill the birds. What do we want to knock out? Two people who don't believe that the coronavirus is serious with one, I don't know, handshake. I think that's a good one. All right. If you would, please go watch video number 60 and then come back and you'll have your third way of finding the greatest common factor. The last one for the greatest common factor is perhaps the oldest one. It is the Euclidean algorithm. Euclid was a very famous mathematician in Greek times. And I have a shirt. It's probably in the closet right here. But I'm way too lazy to go find it right now. And it's got a joke on it. I think that's it. There it is. I'm going to save the image. And I wore this shirt when I was at I don't know where it was. I went to a math conference or I don't know. No, I was just at the store. And this woman asked me, "Oh, are you from Euclid, Ohio?" when she saw the shirt. And I'm not. But she didn't get the joke. You sort of have to say it out loud, and then hopefully it'll make sense. I'll just leave it right there, but hopefully you got it. Anywho, basically in the Euclidean algorithm, what happens... Oh, wait, did I do the wrong one? Oh, I posted the wrong one, everyone! Oh, jeez. Oh, jeez. Cut. Paste. I said paste. Also, I shouldn't hide the text. We should put like a nice little shadow on that. Oh, that's nice. That's good. I like that. That's nice. Okay. Euclidean algorithm. To find the GCF of two numbers, divide the smaller number into the larger. Divide the remainder in the previous divisor and continue until the remainder is 0. The GCF is the last positive remainder. That might not make any sense until we do an example. Also, until we put an even more grandiose mustache on Euclid. There we go. All right, now he's better. All right, so let's pick up some two numbers here. Let's say 366 and I don't know, 52. Do I like those? I don't think I like 52. 54? That's better. So what you do is you take the smaller number, 54, and divide it into the larger number, 366. Now, if you want to use your calculator, that's fine. You can just use long division. I think 6 will work. I don't know if 7 works, but I think 6 works. So that would be 6 is 4, carry the 2, 32. That'd be funny if it worked the first time. Let me make sure, because I don't want to make a mistake. Not that I make mistakes, I'm just saying. All right, 6 does work, so we're good there. So 6 times 54 is 324. Great. So now if we subtract, we get 42. Okay. Since that is not 0, we keep going. 42 goes into the previous divisor, 54. So you take your remainder and put it into the divisor now. This would happen once. Subtract, and we get 12. All right? That's not 0, so we keep going. 12 goes into 42. 3 times. 3 times 12 is 36. Subtract, we get 6. That's not 0, so we keep going. 6 into 12 is 2. Remainder 0. That's great, because now that means we are done. So continue this process until the remainder is 0. Check. The GCF is the last positive remainder. The last positive remainder was 6. So 6 is the GCF. So very weird process. If anything, pretty cool that he figured this out on his own. This is at least 2,000, 3,000 years ago. So great job, Euclid. Yeah. So if you would, please now watch video 61. 61. And then come on back, we'll talk about the LCM. All right, finding the LCM, the least common multiple, using the prime factorization method. So now, the greatest common factor, again, is the biggest number that divides into the given numbers. The LCM is the flip. The LCM is the smallest number that the given numbers divide into. So please watch your prepositional phrasing, because it makes a difference. Okay. The first method is the least common is the prime factorization method. Now, this is very similar to what we did earlier. Let me go back a couple slides. To find the GCF, you take the smallest exponent. To find the LCM, you take the largest exponent. But here's the catch. Only for the GCF, it's what they have in common. For the LCM, it's whatever is available. So here's how you would put both things together. I'm just making this up now. We'll do a nice one, and then a not so nice one. Okay. So this is how both this one method can find both the GCF and the LCM. Okay, for the GCF, notice they both have factors of 2, 3, 5, 7. All right? And for the GCF, you take the smallest exponent. So comparing the powers of 2, 2 squared and 2 cubed, you would take the 2 squared. Comparing the powers for 3, 3 squared, 3 cubed, you take the 3 squared. Comparing the powers for 5, 5 to the 4th, 5 to the 1st, I was taking a 1 here, we would take the 5 to the 1st. And then 7 to the 1st, 7 to the 4th, we take the 7 to the 4th. Hooray! So whatever that number is, 2 squared, 3 squared, 5, 7, that's the GCF. Now on the flip side for the LCM, it's pretty much whatever's left over. So 2 cubed, 3 cubed, 5 to the 4th, 7 to the 4th. Because what's happening is you're looking at the prime factorization, but now you're taking the higher power. Well, you already took out the smaller power, comparing the two numbers, which means what must be left over is the higher power. That's why you can use whatever's left over. Great. Now, that's an example to where they had numbers in common. What if they didn't? I'll put a 2 in here. Okay. If they don't have numbers in common, in my opinion, what you can do is fill in the gaps. So for notice in the first one there, the first number doesn't have 3 to a power. So what you can say is 3 to the 0. Because as we talked about in chapter 4, 3 to the 0 is just 1. And then what else is the first number missing? It's missing an 11. So you can say 11 to the 0. Likewise, the second number is missing a 7 and a 13. So we can say 7 to the 0 and 13 to the 0. So now by doing so, we've met the requirement of what they have in common for the GCF. So by putting in something to the 0, you're just multiplying it by 1. You're not changing the value whatsoever. So with this laid out like this, now it's a little more visual. The GCF would be the smaller power. So for the 2's, you would take the 2 squared. For the 3's, you would take the 3 to the 0, which is just 1. For the 5's, you would take the 5 to the first. For the 7's, you would take the 7 to the 0, which is just 1. 11's, 11 to the 0. And 13, 13 to the 0. The anything to the 0 is just 1. You don't have to write it. So the GCF is technically just 2 squared times 5. So 20. If I did that correctly. Yeah. And then, by this process, anything left over is the LCM. So 2 to the 4th, 3 cubed, 5 squared, 7, 11 squared, 13. Whatever that number is. So this is how the prime factorization can be used to find both the GCF and the LCM. If you would, please try video number 62 for another example of this stuff. Okay, so the last one we have is another throwback. It's dividing by primes. I don't really have steps for this. This again is very similar to what we did previously when we did this stuff here. So if you, I'll just say it this way, you would get down to relatively prime numbers. Where's my cursor? Oh my gosh. If you're finding the GCF, you only multiply these numbers, 2 times 2 times 2 times 5. If you're finding the LCM, you multiply all of these numbers. That's really the difference. So off to the left only, GCF. All the numbers on the outside, LCM. So let's do a full example. Let's say 98 and I don't know. It's so hard to do these in your head. 72? Sure. Why not? Okay. So they're both even, so we can take out a 2. I don't like this. I don't like this at all. I don't like it at all. 84. Should we do 84? Let's do 84. I changed to 84. Okay, so they're both even, so we can take out a 2. This would give us 49, and this would give us 42. All right, we can't use 2 anymore. 7 would be fine. 7 and 6. Well, 7 and 6 are relatively prime, so we would stop. So off to the left here is the GCF. GCF would be 2 times 7, so 14. And then everything on the outside would be the LCM. 2 times 7 times 7 times 6. I don't know what that is. Whatever 14 times 42 is. Okay, Google. What's 14 times 42?
The answer is 588.
Thank you. It's 588. I did that by myself. Alright, so again, prime factorization, dividing by primes, we'll find both the GCF and the LCM. Euclidean algorithm doesn't do a great job with finding the LCM. You technically can do it, and actually this is the halfway of doing it. I'll just mention it now. The other way to find the LCM of two numbers, so A and B, is you would take the product of the two numbers, A times B, and divide it by the GCF. So for example, if we took 98, I don't know why I keep writing the second thing first, times 84, and divided it by 14, the GCF, oh my gosh, that should give us the LCM, which we just found to be 588. So that, I mean, like, that one's not too bad. It's just one more thing to memorize if you want to do it that way. So you could just find the GCF and then multiply the two numbers and divide the two, and you'll get the LCM. That only works if you have two numbers, though. If you have three, that doesn't work anymore. But there's that. Okay, I changed my mind. This video is only going to be 5-4. I'm going to have you watch another video for 5-5. Because I talked about 5-5's material in a college algebra class, but it's the same coverage. So I'll just tell you to watch that video instead. Alright, that's it for 5-4. Lights. Where's my cursor? There it is.